So today I'm going to talk to you about gas laws, which are essentially a group of equations that help us make predictions about the pressure, volume, and temperature of gases and how they relate to each other. So the first thing that you have to understand about gases before you can understand these laws is kinetic theory. Basically, kinetic theory applies to all phases of matter, but we are going to talk about it as it relates to gases. The big main idea of kinetic theory is that all particles are in random motion. So that they also collide with each other. And they collide with the surfaces of a container. In a sense, the surface of a container itself is also made of particles. Since these particles are also in random motion, you have to understand that temperature is actually very much related to motion, because temperature is really the measure of the average kinetic energy of a substance. So if you increase temperature, if temperature goes up, then that means the kinetic energy would go up. So the higher the temperature, the faster the particles will move. Also, the lower the temperature, the slower the particles will move. This is what then led to the creation of absolute zero. Because if we start, say, with 0 degrees Celsius, that's not the coldest that a substance can get. Using some of the equations that I'm going to show you later, scientists thought, well, motion must stop at about negative 273 degrees Celsius. So instead of using a negative number, scientists thought it would be better to use Kelvin. And so that negative 273 degrees Celsius equals 0 Kelvin. And so for the equations that I'm about to show you, you should always convert everything into Kelvin before doing your calculations. Now we have to talk about what pressure is. Pressure is essentially the number of collisions by air particles on a given surface area. So if you feel pressure, or if there's pressure within a container, that is because air particles are hitting it. And so there's the force of those air particles on the surface of that container. A very commonly used measure of, or the units for pressure, are pounds per square inch, PSI. So atmospheric pressure is 14.696 pounds per square inch. So that means if we had a thing that was the size of a square inch, 1 inch all around, that would mean that the force that is hitting that square inch is 14.696 pounds. So this is atmospheric pressure. So right now, if you think about it, your entire body surface is being hit by 14.696 pounds. We don't feel it because we're used to it. Other units of pressure are millimeters of mercury. So atmospheric pressure is 760 millimeters of mercury, which is also equal to torr, so 760 torr. This came from this sort of upside down candy cane shaped barometer, which would have a certain amount of mercury in it. So if pressure increased, the air pressure would force the air down, which then would force the level of mercury up. Also, it would compress this air inside, and so then it was this reading marked out in metric units of millimeters. And so if this was an average day, that level of mercury read along this side would be 760 millimeters. Another unit of pressure is the kilopascal. So at standard pressure, or typical atmospheric pressure, 1.01325 kilopascals. If we think of a pascal is equal to, and those of you who have done physics will know this, is equal to 1 Newton per square meter. And just to review, for those who don't know, 1 Newton is equal to the force of 1 kilogram per meter per second squared. So these are all weird, complex numbers, and so scientists also came up with another unit to be more convenient, which is and probably easier to use, is the ATM. So at our typical air pressure or atmospheric pressure is just at 1 ATM. So if you think of all of these different units, you could also create a whole bunch of conversion factors out of these, where I could say that 1 ATM equals 14.696 psi equals 760 millimeters of mercury equals 101.325 kilopascals. So now that we know what pressure is and we have an idea of how temperature affects the kinetic energy of different particles, we can now start to create relationships between all of these different variables. So Boyle's law is simply this, that if you have a closed container containing a gas, that as the pressure on that closed container increases, the volume should decrease. And so the equation that shows that relationship is this. So basically, if pressure goes up, volume should go down, and vice versa. If volume goes up, pressure would be going down. So you can almost think about a balloon as a good example. If you had a large balloon and somehow you were able to press on it equally on all sides, you would be compressing the gas, and then you would be decreasing the volume. So you would still have, as in a closed container, let's say you started with 5 particles of gas and they're all moving in the same direction or in random motion. You might be able to see how this is related. So if you think about, for instance, each of these particles as being like a ball in a dodgeball game, if you had to play dodgeball in a smaller room, you might feel more pressure because you would be hit more frequently. So the smaller the volume, there's also the smaller surface area of the container. And so it gets hit more frequently. to apply. So basically, if I had 10 liters of gas at 1 atm, and I wanted to know the volume of that gas at, let's say, 2 atm, I could just simply plug in those numbers and then use algebra to solve. In this case, 10 liters times 1 atm divided by 2 atm means that I will have only 5 liters of gas. This is an incredibly important law for anybody who is interested in scuba diving, because as someone descends deeper into the water, the pressure will increase. And so if volume, as you see over here, decreases, then someone will use their air supply much more quickly as they descend. Another law is Charles' law. So again, remember from our kinetic theory that as temperature increases, the kinetic energy of our particles should increase. And so the relationship in Charles' law is that if our temperature increases and we have a fixed closed container, but it does not have, is at fixed pressure, and even though it is a closed container, it is able to expand, then as temperature goes up, then volume should also go up. So this is these two things are directly proportional. So for instance, if we start with a volume of 1 liter and let us say that it is 50 degrees Kelvin, remember that all of our temperatures should be at Kelvin, and we wanted to find out, well, what will our volume be if we are at 100 degrees Kelvin? Well, we do do our algebra, cross cancel, divide. So 1 liter over 100K, or cross multiply and divide, sorry, over 50K. So this ends up being 1 liter times, because our K's cancel out, 100 divided by 50 times 2, we end up with 2 liters. The reason for this, again, let's take our balloon because it easily expands or contracts. If we have our 5 particles that are moving at a certain speed at 50K, but we increase the temperature, so then those particles, since they're moving faster, will be hitting the sides of the container more often. That causes the container to want to expand. And so then that's why this balloon will double in size at 100K, because increased temperature means increased kinetic energy, which means increased frequency of collisions.